Coimbatore. We are thrilled to have you all join us for this insightful program from today till 26th of September 2025, where we will explore the intersections of AI and mathematics with expert speakers from diverse backgrounds. We appreciate your participation and look forward to engaging discussions and learning experiences during the program. Now, I request Mr. V. Ratanakumar, Assistant Professor and Head, to welcome the gathering.
Oh, thank you, ma'am. A very pleasant evening to everyone gathered here. On behalf of the Department of Mathematics, PPG College of Arts and Science, Coimbatore, it is my privilege to extend a warm welcome to all of you to the International Virtual Faculty Development Program on Artificial Intelligence Empowered by Mathematics. We are delighted to host this 5-day program from 22nd to 26th December 2025, bringing together experts from esteemed institutions to share insights on the interplay between artificial intelligence and mathematics. We believe this FDP will provide a valuable platform for learning, discussion, and exploration of cutting-edge topics in AI empowered by mathematical foundations. I extend my welcome to our management, PPG Group of Institutions, for providing a wealthy platform to us. Welcome you all. I would like to welcome our principal, Dr. N. Muthumani ma'am, who have been the guiding light all over the year. I welcome you, ma'am. I extend my warm welcome to our distinguished speakers of this week, Dr. Malia Kumarnath, Assistant Professor, NIT Puducherry, Dr. R. Palpandi, Assistant Professor, Department of Mathematics, NIT Calicut, Dr. Albina, Manager, MS Maria Crestu Cargo Movers, Professor Yang Hui, Fellow, London Institute for Mathematical Sciences, Lecturer in Mathematics, Merton College, University of Oxford, Mr. Karthikeyan, Assistant Professor, Department of CS and IT, Jain University. I especially thank all the speakers for accepting our invite to share our expertise with us. Thank you and welcome you all. I would also like to welcome my faculty members, Dr. Praveena, Dr. C. Janita Nancy, and Dr. A. Maheshwari ma'am to this forum. Welcome you all. We hope you all find the session informative and engaging. We wish all participants a fruitful learning experience and meaningful interaction during this FDP. Thank you all and welcome you once again.
Thank you, sir.
Thank you.
AI is not just about algorithms. It's about understanding intelligence in humans, machines, and perhaps even beyond. I request Dr. R. Praveena, Assistant Professor, to introduce our speaker of today.
It gives me immense pleasure to introduce our distinguished guest, Dr. Malia Kumarnath, Assistant Professor in the Department of Electronics and Communication Engineering at the National Institute of Technology, Puducherry. Dr. Malaya Kumarnath is an accomplished academician and researcher with more than a decade of teaching and research experience. He earned his PhD in signal processing from the prestigious IIT Guwahati. He has also served as a visiting assistant professor at the Asian Institute of Technology, Bangkok, Thailand, under the Ministry of Human Resource Development, Government of India. Dr. Nath has been actively contributing to academics by teaching a wide range of subjects such as digital signal processing, digital image processing, and machine learning. Along with teaching, he has taken on significant administrative responsibilities at NIT, including serving as the Department Academic Coordinator, Project Coordinator, DSB Lab in charge, and Nodal Officer for Digital India initiatives. We are truly honored to have Dr. Nath with us today, and we look forward to gaining from his knowledge, expertise, and inspiring presence. Welcome you, sir.
Yeah, thank you, ma'am.
Thank you, ma'am. Now I request Dr. Malia Kumarnath to take over the session.
Yeah, thank you, ma'am. Good afternoon to all. So today we are going to talk about the mathematical foundation for artificial intelligence as well as machine learning. So whenever we are talking about the artificial intelligence or the machine learning concepts, basically the first idea come to our mind is nothing but the machines or the computers. Whenever we are talking about the computers or machines, basically it deals with the data or the information, or lots of informations, and how we can able to feed the data. Basically, these are in the form of a digital information or the digital data. So the data can be represented in the form of a matrix. The best way to represent the data is the matrix, or we can say a tensors. So if it is a one-dimensional data, the data can be represented by the help of a one-dimensional array. Either it is a column vector or a row vector. Specifically, we are representing in the form of a column vector. So when we are talking about the row vectors, we are just making the transpose of this column vector to represent a row vector. And whenever we are talking about a two-dimensional data, it is in the form of a matrix, consists of m cross n, that means n number of rows and n number of columns. If we are talking about multiple matrices, it is giving rise to a multi-dimensional, or we can say that it is providing the information in a form of the volumes, or we can say it is in the form of tensors also. So today we'll talk about how we can able to analyze this informations, and for the machine learning application. If we are good in the algebra, linear algebra probability, as well as we can able to manipulate these matrices. That means we are good in machine learning and to extract the features for some kind of pattern recognition or kind of deep learning or any other applications. So today we'll look into very fundamental things that is known as linear algebra, vectors, as well as the dimensionality, and how these informations can able to help us in case of artificial intelligence as well as machine learning. As we are talking about the two things together, one is called the machine learning, another is called the pattern recognition, deep learning. So when we are talking about the machine, it basically takes about the data, or it manipulates the data, or it can able to extract the features from the data. So when we are talking about the pattern recognition, basically it is the technique to recognize the various patterns or various kind of representations, and how it can be represented. It can be represented by the help of certain kind of information that is extracted from the pattern. So I'm giving a very simple example to you. If you are not, that means whenever we are talking with our mothers or parents, basically we can able to identify the mother's voice, even if the mother is having a throat pain or some throat infections. How we can able to identify? This is nothing but the patterns. The aim is of this today's discussion is that how machine can able to identify the patterns. The way the human can able to identify the patterns, the way the machines can able to identify the patterns. Whenever the machines is identifying the patterns, it is basically extracting the information that is known as the features from the patterns. Basically, how the features are extracted, as I have discussed, the data can be represented in the form of the matrices. Either it can be represented in the form of a column vector or a row vector, or it can be represented in the form of a matrices. So now we'll talk about how this will help us to provide the deep insight into AI as well as machine learning and deep learning concepts. The fundamental process that we are representing the features. So how we can represent the features? Already I have given the idea that we can represent the features from these matrices. So today we'll talk about very simple information, so that is in terms of norm, distance function, scalar product, linear independent, matrix operation, Haramada product, as well as element divisions. I hope a few of the things is known to you, and it is already taught in terms of mathematics. So when we are talking about the vector, basically the vector x of dimension d is represented by this representation. So this is whenever we are talking about a vector, it is nothing but a column vector. So x1, x2 up to xt. If we'll take the transpose of this vector, that will give rise to a row representations. So what vector basically represent? A vector space is defined as a non-empty set of entities called vectors and associated scalars that satisfy the condition A to C, and discussed in the next slides. So as we are talking about the vectors, it can be a real or or it can be a complex. So complex means that means it consists of both real as well as imaginary part. So we are talking about the conditions. What are the conditions? There is an operation called vector addition is possible. That means if we'll add the two vectors that is equal to x and y, this will give rise to another vectors. So if in a vector space or in a space, if x plus y must be equal to y plus x, and it also satisfies the condition of associativity. So that is equal to x plus y plus z is equal to x plus y plus z for all x, y, and z. So in the vector space, there is a unique vector is representing or present that is known as the zero vector. If we add the zero vector to the any vector, we are getting the same vector. So that is equal to x plus 0 is equal to x, or 0 plus x is equal to x. There is a vector is existing that is known as the negative vector. If we add x plus the negative of x, that will give rise to 0, or negative of x plus x, that is equal to also. So these two conditions, that means the condition A to be satisfied. What is the condition B? That means the operation multiplication by the help of a scalar. So it is associated with each scalar C, and each vector x is called the product of C and x, which is represented by C of x or x of C, and which satisfy the following conditions. That is equal to C into D of x, that is equal to, so we can say that C plus D into whole x multiplied, that will be represented as Cx plus dx. Or we can say a constant C is get multiplied with the addition of the two vectors, that is equal to x plus y, that is equal to Cx plus Cy for all the scalar C and all the vectors x and y respectively. The condition C says there is a unity vector 1 that is existing in such that 1 into x must be equal to x, and this is applicable for all the vectors. So we are interested in particularly in real vector space of real m cross 1 column matrices. Such spaces are denoted by R of m and defined by vector addition as well as multiplication by the scalars. So as we have discussed in our previous slides, that it can satisfy some conditions. So that means a vector space is defined as a non-empty set of entities called vectors and associated with scalars that satisfy the condition A to C. So the condition A we have seen, which is with respect to the addition. Condition B is with respect to the multiplication, and condition C, that means it represents a unity vectors. So that means it should satisfy the condition A, B, and C. So here we have represented the very basic example that is consists of two vectors, that is equal to A is a vector and B is another vector. So in this case, this A vector is represented by 2, 1. So that means it has 2 units along the that is equal to x direction and 1 unit along the y direction. So 2, 1, and B is equal to nothing but the another vector which is represented by 1, 3. So that means this is equal to 1 and this is nothing but equal to 3. So if we add these two vectors, that is equal to A and B, so this will give rise to A plus B. So which is nothing but is represented by this vector, that is equal to 2 plus 1 and 1 plus 3, which will be represented as 3, 4. So that means 3 is along the x-axis and 4 is along the y-axis. In the similar way, we can able to perform the subtraction operation over the vectors, that is equal to, if we subtract it, that means B has to be subtracted from A. So now this is equal to A vector and B, which is nothing but that is called the negative of this B, it will come in this direction, that is equal to minus B. So now the resultant vector will be represented by A minus B, which is nothing but if we perform the mathematical representations, that is 2 minus 1, 1 minus 3, that will give rise to 1 as well as minus 2. So this 1 is representing along this x-axis and minus 2 it is representing along this negative direction of x, that is 1 minus 2. So this is the graphical representation of the vector addition as well as the subtractions, and similarly we can able to perform the multiplication also. So whenever we are representing the vectors, the vector can be represented by the norm. Why it is why we are interested in the norm? Basically it will provide one of the features, that is what is the magnitude of the vectors. So basically the norm will represent the length of a vector and which or it functions which maps a vector into a real number for a given vector space. That is, x mod is greater than equal to 0. So or x is equal to 0 for the value x is equal to 0. So there is a scalar alpha is existing such that we can multiply alpha with the vector x that will give rise to alpha mod with x mod. And this vector also satisfy the triangle inequality properties, that is equal to x plus y norm must be less than equal to x norm plus y norm. So if we represent the LP norm, that means the xp, that means the vector x is consist of x1, x2 up to xd. So now the LP norm can be represented by x1 to the power p plus x2 to the power p plus up to x2 to the power p to the whole power 1 upon p. So that means in this case we are considering, if you will consider p is equal to 2, then it will become equal to x1 square plus x2 square plus up to xd square to the power of 1 upon 2. That means we can say that this is nothing but the root over of x1 square plus x2 square plus up to xd squares. So in this case, we are calculating the Euclidean norm of these vectors. If 0 is less than q is less than p, then we can write that is equal to xp is equal to less than equal to xq is less than equal to m to the power 1 upon q into that is minus 1 upon p into x to the power p. So in this case, we can say that m of 1 upon p minus 1 upon q xq must be less than equal to xp is less than equal to xq. So maximum L infinite norm represent x of infinite, that is equal to maximum of
Yes, sir. Sir, your voice is not audible, sir. Sir, are you there?
Sir, we cannot able to hear your voice, sir. Excuse me, sir.
Ma'am, please hold on, ma'am. Sir is leave the meeting.
Yes, sir.
okay. Am I audible?
Yes, sir, you're audible, sir.
Sir,
Yeah,
you're audible.
that internet is disconnected. I don't know. There
Okay.
may be some problem.
No
Yeah.
issues.
So as we are
No
talking
issues, sir.
about the vectors. So that means it is represented by the distance functions. So the metric D defines the distance between the two vectors, and it is always positive. That is equal to D of xy is greater than equal to 0. And it is symmetric. That means we can say that D of xy is equal to D of yx. The transfer inequality is D of xy is less than equal to D of x plus which already know it. And the distance between 2 points can be represented by dpx, y, that is x minus y, not p, that can be represented as x1 minus y1 to the x2 minus y2 to the power p, or to 3 minus yd to the power p. So if p will be equal to 2, to represent the Euclidean distance between the two vectors. So we are talking about LP naught, distance between two vectors x and y. X minus y, p. So then this will that means this equation will boils down to taxi curve, or that is known as the Manhattan distance. So the Manhattan distance between the two vectors is represented by x1 minus y1, x2 minus y2 up to xt minus yd. So this basically represent the L1 norm. So the L1 norm are represented in a simplest way, that is summation j is equal to 1 to d x minus to the power p raised to or summation j is equal to 1 to d x minus the
So sorry for the interruption, sir. The voice is breaking, sir.
So it is product is 0. So orthonormal vectors represent orthonormal vector.
Sir, Malaya, sir.
Yes. Any questions? Yeah.
Sir, your voice is breaking, sir. So can you hear me? Malaya, sir.
Yeah. Is it now? Am I? Yes.
Sir, your voice is not clear, sir. It's breaking.
Voice is not clear. Okay. Let
Kumar, sir. Sir, your voice is not audible, sir. Can't hear your voice, sir. Please enable your microphone, sir.
It is audible?
Oh, okay, sir. Okay, fine, sir.
Yeah, okay,
That's
fine.
good. Thank you.
The slide is visible? Slide is
Yes, sir.
visible? Yeah.
Yes, sir. Yes, sir. It's visible.
Yes, sir.
Yes. Yeah, fine. So as we are talking about the matrix operation, so the multiplication is not commutative. That means already you know from this matrix A dot B is not equal to B dot A. Why we are talking about this matrix multiplication, transpose, and all this information? Because when we are talking about this machine learning or the deep learning concepts, basically we are using some convolution operation, some correlation operation, and basically this convolution operation, correlation operation are used to extract the features. And these features can help in identifying the patterns, or can able to identify some important information related to the patterns. So now here we are talking about the transpose that is equal to A dot B, whole transpose is equal to B transpose into A transpose. Or we can write that A dot B is equal to B transpose into A transpose transpose. So what is symmetric matrix? The symmetric matrix is the matrix in which the transpose of the matrix is equal to the original matrix. The identity matrix represent the diagonal elements are all one, and the off diagonal elements are zeros. Orthogonal matrix is a matrix where the dot product of the A transpose with A or A with A transpose is equal to the identity matrix. So if we perform the simplification over this, we can write that A inverse is equal to A transpose. You can verify yourself whether this matrix is a symmetric matrix or not. Next is the Hermitian matrix. A real symmetric matrix is a Hermitian if all its eigenvalues are real. That means we can say that the matrix is a Hermitian if and only if A is equal to A conjugate transpose. So now if we take the conjugate transpose of the matrix and we are getting the original matrix, then this matrix is called the Hermitian matrix. So you can verify whether this matrix is a Hermitian or not. Similarly, the unitary matrix represent the inverse of a matrix is equal to the conjugate of the transpose. So now if we multiply A into A conjugate transpose, now A conjugate transpose, I will substitute that is equal to A inverse. So I can write A into A inverse is equal to the identity matrix. If this condition is satisfied, then we can say that the matrix A is called the unitary matrix. So here one example has been illustrated. You can verify yourself that whether the matrix is unitary or not. Similarly, we can talk about the orthogonal matrix that is equal to A inverse is equal to A transpose. In other words, we can say that A into A transpose. Now substitute the value of A transpose is equal to A into A inverse, that is equal to the identity matrix. One example has been illustrated to show the orthogonal matrix. So here there are some problems. I'm just skipping these problems. Now we'll talk about the already we have discussed what is called a unitary matrix. So now next is the Topli's matrix. What is this Topli's matrix basically represent? If the main diagonal and the sub diagonals contain the constant or the same elements, then that matrix is called the Topli's matrix. The system matrix corresponding to the linear convolution of the two sequence is a Topli's matrix, and convolution is one of the most important operation that is performed in case of the deep neural network or deep network that is deep learning to extract the features from the data. So now what exactly this Topli's matrix represent? The system matrix corresponding to the linear convolution of two sequences. If you are performing the linear convolution of the two sequences, it will give rise to the Topli's matrix. Now what is convolution? Basically, if you are having the two vectors, or we can say that two signals of a different length, then what we have to do, the convolution says perform 180-degree rotation of this the smallest duration or the smallest length signal, then multiply and shift the rotated signal over the unrotated signal and multiply the overlapping regions, and that will provide the convolution output. Now we'll see whether this convolution that is called the linear convolution provides a Topli's matrix or not. Now here the example has been illustrated to show this matrix Mn, which consists of m number of rows and n number of columns, each a tuple. So if you look into the main diagonal, that is consist of the constant elements of the same element, that is equal to A0. Similarly, this diagonal is consist of the same element, that is equal to. Similarly, this diagonal is consist of same. Similarly, this one, and this process is there. So that means the constant element along the main diagonal and the sub diagonal is known as the tuplage matrix. Now we'll understand this by the help of an example, that is the linear convolution as a tuplage matrix operation. So in this case, h of n is equal to n, and n is varying from -1 to 1, and x of n is equal to 0, which is outside the range, that is equal to 0 less than equal to n is less than equal to 4. So now we have to find the convolution output, that is equal to y of n. So y of n can be represented as h of n convolution with x of n, that is represented by summation k is equal to 0 to n minus 1 h of n minus k into x of k. So in this example, we have taken h of n, that is equal to n, and it is lying from -1 to 1. So that means if n equal to 0, this will value is equal to 0. If n equal to -1, it is equal to -1, and n equal to 1, this is equal to 1. And x of n is equal to 0 outside the range. That means it is existing from 0 to 4. That means the xn has a value for x of 0, x of 1, x of 2, x of 3, as well as x of 4. Now we want to perform the convolution, that is equal to yn is equal to hn convolution of xn. So now the linear convolution says that is equal to summation k is equal to 0 to n minus 1, that is equal to n minus 1 is equal to 4 h of n minus k x of k. Now if we substitute the value of h of n as well as that is and x of n in this expression and go for simplification, that is equal to k is equal to 0. So this will give rise to h of n x of 0. If k is equal to 1, so this will be h of n minus 1 x of 1. If k is equal to 2, this will be h of n minus 2 x of 2. If k is equal to 3, that is equal to h of n minus 3 x of 3. If k is equal to 4, that is equal to h of n minus 4 x of 4. Now already you know what is the value that is equal to x0, x1, x2, x3 up to x4. So now we can write this is a multiplication of two matrices. So now if we substitute the values, that will give rise to h of n. What is h of n? If n equal to 0. So now this will give rise to 0. If n equal to 1, what is the value? N equal to, that is equal to, we can say n is equal to 0 here. So n of 0 is equal to 0. If n is equal to 0, so this will give rise to h of minus 1. H of minus 1 is equal to minus 1. So n is equal to 2. H of 2 or minus 2, that is equal to h of 0. So again it will be 0. So next is equal to h of n minus 3. So that means 0 h of minus 3 is not existing, that is equal to 0. H of minus 4 is equal to 0. So now h of 0 is get multiplied with x of 0. H of minus 1 is get multiplied with x of 1. H of minus 2 is get multiplied with x of 2. H of minus 3 is get multiplied with x of 3. H of minus 4 is get multiplied with x of 4. So I can write this is the representation of the multiplication of two matrices. Similarly, we can take that is equal to n is equal to 1, and we can go for simplification of this. So now after this, we can say that this is the matrix, which is nothing but the diagonal elements as well as the off diagonal elements are all equal. So this is the diagonal element, all zeros. This is an off diagonal element consists of minus 1. This is the off diagonal element, again 0. So similarly, this is the that is called again the diagonal element consists of all 0. This is again diagonal element 0. This is the diagonal element 0, and this is. So that means what tuplage matrix is representing? The tuplage matrix represents the diagonal as well as the off diagonal elements are having the constant value, and basically the linear convolution output is represented by a tuplage representation. Now what is circulant matrix? This circulant matrix plays a very vital role that the any one column or any one row can be represented by the circular representation of the previous row or the previous column. So if we'll take any of the row, so suppose I will consider this row elements can be obtained by the circular shifting of this previous row. That means if I will consider a of n minus 1 at the beginning, then it will become rise to or give rise to a of n minus 1, a0, a1 up to a of n minus 2. Similarly, these row elements can be obtained by the circular shift of this previous row. Similarly, if you will consider any of the column, that is equal to, if you will consider this column that is consist of a1, a0, a of n minus 1 up to a2. So this column can be obtained by the circular shift of this row. So that means this a0 will be coming here, so and this will be shifted. So it can be represented as the circular shift of the previous row or the previous column, and which is mathematically represented as a of mn, that is equal to a of m minus n modulo n. So now, where exactly we are getting the circular, that means a circular matrix. Circular convolution as a circular matrix operation, if two convoluting sequence is periodic, then their convolution is also periodic. In a previous case, we have discussed that the linear convolution. But in this case, we are talking about the circular convolution. The circular convolution says the two elements or the two sequences are circular in nature. So due to circular in nature, we can get circular output, or that is called the circular matrix. So similarly, the diagonal representation. The diagonal representation says we can represent any matrix by the representation of the eigenvalues as well as the eigenvectors, or we can represent it in the form of eigenvalue decomposition or the singular value decomposition. The eigenvalue decomposition as well as the singular value decomposition says the decomposition of a matrix, and this decomposition helps in performing the compression or data compression in case of machine learning or pattern recognition. And basically in this case, in case of eigenvalue decomposition, or we can say the eigenvalues, a of phi k must be equal to lambda k phi k, where phi k represent the eigenvectors and the lambda k represent the eigenvalues. So that is a of phi k is equal to lambda k phi k. So what exactly this lambda represent? They basically represent the energy content of the matrix. So that means if you multiply all the eigenvalues, it will provide the determinant of that matrix. The eigenvalues having the highest values are basically representing the data, or basically are used for reproducing the data, and this helps in case of data compressions. If we look into the block matrix, basically it is a matrix whose elements are represented by matrix themselves. That means we can say that the individual elements are again the matrices. So this kind of representation is called the block matrix. Whenever we have to form the bigger matrix, we can able to represent a block matrix. Similarly, in this case, we are talking about the Topli's block matrix as well as the circular block matrix. Next is the Kronecker product. The Kronecker product says that is the A Kronecker B. If A and B are the two matrices which are represented by M1 cross M2 as well as N1 cross N2 matrices, then the A Kronecker B defined as that will be represented by these representations. And this Kronecker product that is A Kronecker B is not equal to B Kronecker A. A Kronecker B multiplied with C Kronecker D can be represented as AC Kronecker with BD. So now we'll understand this by the help of an example. Suppose A is nothing but the matrix which is whose elements are represented by 1, 1, 1 as well as minus 1, and B is another matrix whose elements are represented by 1, 2, 3, and 4. Now I have to perform the A Kronecker B. It will be represented by A Kronecker B. That means the first element of A is get multiplied with the complete matrix, that is equal to 1 is get multiplied with B. So this will give rise to 1, 2, 3, 4. Similarly, this 1 is get multiplied with 1, 2, 3, 4. So this will give rise to 1, 2, 3, 4. This 1 is get multiplied with 1, 2, 3, 4, 1, 2, 3, 4. And this minus 1 is get multiplied with 1, this B matrix, that is 1, 2, 3, 4. This will give rise to minus 1, minus 2, minus 3 as well as minus 4. So now, if we'll perform the B Kronecker A, then we'll get this matrix, and we can easily prove that A Kronecker B is not equal to the B Kronecker A. So there are certain properties of this Kronecker product that has been summarized here. Similarly, there is a Haramada product also present. I'm just skipping this Haramada product. Next, we will talk about the tensor product. Suppose A and B are the two that is called vectors. That is A tensor B can be represented as A11 multiplied with B and A21 multiplied with B. So that will give rise to this representation. If a B tensor product with A, that will be represented by B11 multiplied with A, B21 multiplied with A, that will be represented by this representation. So this is the tensor product for the matrix. The similar way we can able to calculate the tensor product. So next we'll talk about the matrix calculus, which represent the gradient, Jacobian as well as Hessian matrix. And it is very important in case of machine learning to calculate the gradient. Basically the gradient is used to update or to calculate the weights such that we can able to reach at the optimum value. So in other words, we can say that we have to find the value of weights in such a manner that the mean square error between the actual output and the predicted output will be equal to 0, or it will be the difference between them is very, very small. So we can say that the gradient, it consider a continuously differentiable function that will be represented by the gradient vector that is equal to delta. That is derivative of this function f of x with respect to x1, derivative with respect to x2, derivative with respect to x3. So now the gradient operator is applied over the function that is equal to f of x is equal to y. So in this case, we have to calculate the gradient of this continuously differentiable function that is equal to f of x, that is derivative of f with respect to x1, derivative of f with respect to x2, as well as derivative of f with respect to the x3. So what are the rules of this gradient? This will satisfy the distributive property that is equal to gradient of A multiplied with fx plus B multiplied with gx can be represented as A gradient of fx plus B gradient of gx. For a bilinear form, this gradient can be represented as x transpose A into x must be equal to A transpose plus A into x. If A is a symmetric matrix, this gradient can be represented as gradient of x transpose AX is equal to 2AX. For a scalar product, this will be represented by this representation. Next, we'll talk about the Jacobian. Which basically represent the generalization of a gradient for a vector valued function of a several variables. So now consider a continuously differentiable function that is represented by f of x. Then the Jacobian can be represented as a derivative of f with respect to x1, derivative of f with respect to x2, derivative of f with respect to xt, the transpose. Now we can say that this f that is equal to f1, if this is a function that is equal to f1 with respect to x1, derivative of f1 with respect to x2, derivative of f1 with respect to xt. Similarly, we can able to compute that is derivative of f2 with respect to x1, derivative of f2 with respect to x2, and derivative of f2 with respect to xt. Similarly, we can calculate the derivative of fk with respect to x1, derivative of fk with respect to x2, and derivative of fk with respect to xt. So in this case, the Jacobian of f is represented by a k cross d matrix, which is represented by this representations. So this Jacobian can be represented by this representation that is equal to the gradient of f of x transpose. Next is called the Hessian matrix. Consider a continuous double differentiable function that will be represented by this representation that is equal to f of x is equal to y. So the Hessian matrix of x that is represented by the gradient square f of x, or that is known as the Hessian. So that will be represented by del square f of x that is equal to del of f with respect to x1, del of f with respect to x2. The transpose, that is nothing but the Jacobian of this. So that will give rise to the that is a derivative square f of f1x that is equal to del x1 del x1. So del square fx with respect to del x1 del x2, del square f1x that is del of x1 del of xt. So this will be applied to all these functions that is equal to f1 f2 up to fk, and we are getting this matrix which is nothing but the Hessian matrix. So the Hessian matrix can be represented as the gradient square f of x that is equal to Hessian of f of x, or in other we can say that the gradient is nothing but the gradient with respect to f of x. So we can calculate the Jacobian of the gradient, that is equal to Jacobian of the gradient of fx with respect to the transpose, that is give rise to the Hessian matrix, that is equal to del square fx, that is equal to h of fx, and Jacobian of that is the gradient of fx transpose. So next is called the gradient based optimization. What is this gradient based optimization? Basically it tells we have to reach at the optimum value in the space, so that we can reach at the minimum point, or we can reach at the minimum point in such a manner that the predicted value must be equal to the actual value, so that the error has to be minimized. So this is basically represent the gradient based optimizations. I'm not spending much time here. So there are some points just look into that and get more details about these points. So this is called the Newton's methods of dating rule must be equal to xn minus eta del of f xn. And the second order optimization is representing the Hessian matrix, which is nothing but the Newton's best method, that is equal to x of n plus 1, that is equal to xn minus hn inverse del of f xn. So now, in this case, we are talking about the two optimization techniques. One is called the gradient-based optimization, and that is called the first order optimization, and the second is called the second order optimization, which uses the Hessian matrix. So Hessian matrix as well as gradient is used for the optimization purpose. So now we are talking about the machine learning perspective, that where exactly and why we are exactly require the optimization. Suppose I have an equation y is equal to represented by some kind of m into x, plus c. So this is the equation of a straight line having some intercept, or this intercept can be represented by the distance from the origin. Now we have to find the value of m as well as the c, because x is the input, or we can say independent variable, and y is the dependent variable. Now we have to adjust the value of m and c in such a manner that we can get the predicted output. Now this predicted output must be equal to the actual output, that is equal to y. In other words, I can say that y minus y hat must be equal to very, very small. That means the error between them is equal to very, very low, that is equal to 0. So now how we can able to get the optimized value of m and c? This optimized value can be able to compute if we are calculating the gradient of this error with respect to m, or take the derivative with respect to m as well as c. So we can get the optimum value of that is called the weight, that is or we can say that is the slope, as well as the derivative of this that is called intercept or the bias. So we can able to calculate the optimum value of m as well as the optimum value of c by the help of the gradient descent, or by the help of the second order. So what are the dilemmas in machine learning? Basically, the dilemmas represent the cause of high dimensionality, which negatively influences most of the machine learning algorithms. So machine learning working with a low dimensional data and may not work with a high dimensional data. So the rounding problem leads to wrong results or errors during the computation process. So the course of dimensionality was initially introduced by the Richard Bellman. It represents the surprising effects. That means analyzing and organizing the data in a high dimensional space. The geometric concepts are more familiar in lower dimension compared to the higher dimension. So that is the course of the dimensionality. So the efficiency and effectiveness of the machine learning algorithm is deteriorating as the dimensionality of the data increases exponentially. So that means in order to make this efficiency and effectiveness of the machine learning algorithm to be appropriate or to be a desired level, so you have to work in a lower dimensional. But sometimes we have to increase the dimension to make the data to be more separable. That means the data points become sparse in a high dimensional space and making it difficult to represent as a meaningful pattern. So a vast amount of data is required to sample the space. The problems or the course of dimensionality represent the increases the computational complexity. It requires a longer training time. It is a higher resource requirement, escalates the risk of overfitting, the spurious correlations, the generalization ability of machine learning algorithm is hindered due to the unseen data. The process to overcome the course of dimensionality is known as the dimensionality reduction. One is called the feature selection as well as feature extraction. There are some data processing techniques are used by the researchers such as normalizations and the handling of the missing values. When we are talking about the feature selection, there are multiple kind of techniques have been used to extract the features. One of the best way is called mean, median, variance, kurtosis, negentropy, differential entropy, entropies. There are multiple kind of entropies are basically used to extract. Similarly, we are talking about in case of a Fourier domain that is called DFT, wavelet decompositions, principal component analysis, singular value decompositions. Next is called the wavelet decomposition, Gopper filter. So these are multiple kind of feature extraction techniques people have used to extract the features from the data, as well as the feature selection. The most important that how we can able to select the features from the data. So there are multiple feature selection techniques are there to identify the best feature. One of the most important technique is called the MR technique, optimization techniques, etc. The data processing represent the normalizations and how to handle the missing values of the data. As we are talking about the dimensionality reduction, so in dimensional reduction, there are two things are there. One is called the feature extraction, another is called the feature selection. Basically, the feature selection represents the identify and select the relevant features by discarding irrelevant or the redundant ones. It reduces the dimensionality of the data, simplifying the model and improving its efficiency. Feature extraction says how we can able to extract some useful information from the data. There are many techniques people have used. A few of them have been represented here: PCA, linear discriminant analysis, singular value decomposition, discrete cosine transform, TSNE plot, autoencoders. There are multiple things people are using for the feature extraction. The normalization is used in case of data processing. The scale the features to a similar range to prevent certain features from dominating the others, and especially in case of distance-based algorithms, handling missing values. That means it able to address the missing data appropriately through imputation or deletion to ensure the robustness in the model training processes. So the course of dimensionality, how we can represent mathematically the course of dimensionality, that is analyzing and organizing the data in a high dimensional space, speciality, the volume of the space, and increases exponentially in a higher dimension. Let us consider one example: a line in 1D having the 10 points. That means it represents the 10 integers. But when we are talking about a two-dimensional, it represents a square with 100 cross, that is 10 cross 10 points, that is equal to 100 points. So that is 10 to the power 2. If we take the consideration of 80 dimension, that means it will give rise to 10 to the power 80 points. So that means as we are increasing the dimensions, that means the information or the data or the points will become more sparse. So that means that is the whole idea. The increasing the dimension increases the volume exponentially. That is, the data points become very, very, very sparse. So that means most of the space is empty. So that means it is very difficult to represent the dimension. That means or realize the volume or realize the model in a higher dimensional space compared to a two-dimensional or compared to a lower dimensional. In case of 1D, a hypercube is a line segment that is from 0 to 1. The distance is 0 to 1. But in case of 2D, this is represented by a hypercube that is a square. Distance between opposite corners that is represented by √2, according to the Pythagorean theorem. If you look into the d-dimensional, this is represented by √over of n. So increasing the dimension to n increases the largest distance within the hypercube and grows at the order of √over of n rate. And this phenomena illustrates the diminishing return effect, that is the smaller gains in spatial distances. So the important points that we can able to summarize here, that a hypercube in d dimension has 2 to the power d vertices, and the volume of a hypercube increases exponentially. Analyzing and organizing the data in a high dimensional space is difficult, and geometric concepts are more familiar in case of a lower dimension compared to the higher dimensions. So this is shows how the nearest point and farthest points are represented in a lower dimension as well as the higher dimensions. So if we are going increasing the dimensions, so how the nearest point and the farthest points look like. So this diagram represent the dimension along the x-axis and the distance between the nearest and farthest point in a the distance between the nearest and farthest points. So as the dimension is very low, the distance is higher, but as the dimension increases, so the distance also reduces. So this is what exactly the relative difference between the nearest and the farthest point tends to decrease with an increase in dimension. So points are sparse in high dimensional space. This can be represented by n ball structure. So this is the variation of the n ball. So I'm just skipping this. So this is the representation of the volume of a ball in an n-dimensional space. So now look into some of the questions and try to answer by yourself. That what we have learned during this short span of time. There are many things that we have to discuss, but due to time shortage, we could not able to discuss. Why does the course of dimensionality occur? So basically, this leads to adding more features or dimension, increases the complexity of the data without increasing useful information. So in high dimensional spaces, most data points are at the edges or the corners and making the data to be very sparse. Why is the course of dimensionality a problem in case of machine learning? Because it leads to overfitting condition and increases the computation and data sparsity. The challenging to derive a meaningful information from the data is difficult. Can we always use the dimensionality reduction to solve the course of dimensionality? No, it is not always suitable to make the dimensionality reduction in case of machine learning. There are many techniques people are using to perform the dimensionality reduction. One of the technique is the singular value decompositions, eigenvalue decompositions, discrete cosine transform, wavelet decomposition, Gauer filters, etc. So few of them are there. Due to time shortage, we are not discussing all these terms. Does more data always represent a better ML? Depends upon the quality as well as the relevance of the data, not the quantity of the data to be used. Are the dimensionality reduction technique is linear? PCA and TSNE help to visualize the data. If we talk about the linear representation, one is the PCA and LDA. If you look into the non-linear representations of these dimensionality reductions, that is called autoencoder, locally linear embedding, TSNE, isomap, kernel PCA, etc. What is dimensionality reduction? Already we have discussed the process of reducing the number of input variables or the features in a data set while preserving as much as relevant informations. If we look into one of the simplest example, in case of eigenvalue decomposition or the singular value decomposition, we are considering only a few number of eigenvalues to represent the data. So, or if we talk about the discrete cosine transform or discrete sine transform, we are representing the data by the help of less number of coefficients. So, exactly what it represents the reduction of the size. What are the approaches to dimensionality reduction techniques? That is the high correlation filter, low variance filter, missing value ratio, random forest, backward feature elimination, factor analysis, and projection methods. Forward feature selection, linear discriminant analysis, independent component analysis, principal component analysis, general discriminant analysis. These are few of the techniques. What are the advantages and disadvantages of dimensionality reductions? So if we'll go for the dimensionality reduction, it will improve the quality, it prevents overfitting, it provides better visualizations, reduces the cost of dimensionality, etc. If we look into the disadvantages, basically the information is lost, it increases the error. Choosing the right feature is very important in case of dimensionality reduction. So how the dimensionality reduction work? Redundancy is present for the direction in the high dimensionally is reduced. What are the feature selection techniques? So if you look into the different feature selection techniques, MR, that is filtering based method, Pearson correlation based methods, approaches are there. What are the feature projection techniques? So if you look into the feature projection techniques, these are few of the techniques are PCA, LDA, TSNE, uniform manifold approximation and projection, multidimensional scaling, autoencoders. These are the few of the techniques. What are the hybrid methods? If you look into the hybrid methods, that is factor analysis, multiple correspondence analysis. What are the graph-based methods of dimensionality reduction? That is isomap, locally linear embedding, Laplacian eigenmap, etc. What are the specialized approaches for dimensionality reduction, such as the independent component analysis, non-negative matrix factorizations, etc. So these are the few of these literatures have been used to prepare the slides. Just to have a look into these references, you can get more detail about the mathematical foundations for the artificial intelligence as well as machine learning. Any questions? We can have a discussion. Yes.
Thank you, sir.
Yeah.
In mathematics, the art of asking questions is more important than the art of solving problems. I request the participants to raise their queries.
In my slide, my email ID is present. If you have any queries, you can send email also to me to get more detail about this. We can have a discussion.
Sure, sir.
Madam, sorry, I have another class actually. So I have to just go to
No
the class.
issues, sir. No issues.
Yeah.
Yes, sir.
I have a small request to all the participants. If you have any queries, any sort of doubts, you please send a mail to me. I'll happy to clarify your doubts or clarify your questions.
So finally, we have vote of thanks, sir.
Yeah, okay.
Now I request Dr. A. Maheshwari, Assistant Professor, to deliver the vote of thanks.
I express my sincere thanks to the management for this constant support and guidance for the smooth conduct of this program. I feel honored to mention my gratitude to our principal, Dr. N. Muthumani Madam, for her perceptual support and constant encouragement to conduct this function successfully. I express my deepest gratitude to our speaker, Dr. Malaya Kumarnath, for this insightful speech to the participants. Thank you, sir. A big thank you to our fantastic participants in the first session of our FDP. Your engagement and insights were invaluable. Once again, I thank you for all the participants. Thank you all.
Thank you, ma'am. Participants, a feedback link has been put up in the chat box. I request all the participants to fill out the feedback form. Feedback link will be closed after 10 minutes. With insightful discussions on introduction to AI and the role of mathematics today, we wrap up day 1 of the International Virtual Faculty Development Program on Artificial Intelligence Empowered by Mathematics. Looking forward to tomorrow's session on Mathematical Foundations on AI. Thank you to all the participants for your engagement. Thank you all once again. A gentle reminder, a feedback link has been put up in the chat box. I request all the participants to fill out the feedback form. Feedback link will be closed after 10 minutes. Thank you all.